Hello everyone, this is Anil and you are watching the YouTube channel Neil Classes. So I welcome you all in my YouTube channel. If you are new on this channel, then I request you to subscribe the channel, like the video, give your comment, and if possible, then share the video with your friends. So now we are studying Lagrangian Dynamics, and in last class we have seen that Lagrangian equation of first kind, and in which one we introduce even term the Alembert equation principle, Alembert principle, which is we can apply minus p dot, or here we added one, then I to 3n and lambda times rho phi by q I, and this one we can consider alpha. Here in the multiplication it was q I is equal to 0. This equation we have drawn, and we have seen that if we keep that value of we have to keep the value of lambda such that all the k terms which are dependent all should get vanished or finished. So we will get independent coordinate that will be remaining. So in this one, by getting this equation, we got the one benefit that we got benefit that means using this equation we don't need to worry about constant force, because constant independent coordinates due to the constraint all will get finished and we will get independent coordinates then, so we no need to worry about that constant force. So generally we can solve that equation. Second, if as it have that advantage as well as it's having disadvantage also, because there are means if you are taking a small means consider number of constraints are less. If less, then no need means then we can keep the value of lambda, like if number of constraints is 1 or 2, we can keep that value of lambda. But what if the number of constraints are more in any function? So that time it will be difficult to means for each constraint we have to imagine that lambda value, and according that you have to keep. So that time means work is a tedious work, or that is difficult to solve that, and it's take time also. So for that one, it means it's having disadvantage. So this equation, after solving this equation, what that Lagrangian who means sent that concept to the Euler, that time he was the great mathematician. So Euler, after reading the Euler's this equation or this principle, this idea, he got means he liked this idea and he also worked on this, and again they both worked on that D'Alembert equation. D'Alembert principle, and then like this is the D'Alembert principle. So on this one they worked again. Why did they work? Because as well, if we are doing anything, means we made this equation to solve the easy work, maybe it should be easy to solve. But thing is that we have to face difficulty again and again. So that is not it was not having much use. So they worked then on this equation they had to work, because in that equation if you see we are directly or indirectly we are depending on constraint. We have to think about constraint. So this is not a correct solution for that. So that's why they worked on again on D'Alembert principle, and they both got on that equation, or which is known as a Euler Lagrangian equation. So now today we will start that how will they got Lagrangian equation. So they use this formula only. By using this formula, they got an equation that is called Euler Lagrange equation. So what did they do? If I keep it inside, like applied force and minus p dot, yeah, this equation they use, and this one. If you are keeping here 1, 2, if n number of particle is there, then it will be 3n. So here also we can keep 1, 2, 3n on here also sigma equal to 1 to here. So they use, means what did they do? They solve this part of this equation separately, this part of the equation separately. So let me make it part number 1, part number 2. Part number 1, part 2 means we will use this term like I is equal to 1, 2, 3 n or Ri is equal to, we will solve this one. The value we will get, we will keep it here. Similarly, we will keep solve this one means term, and the value which at last we will get, we will keep it this one. So basic idea I can give that here what we will do, we will try to keep the dr here, dri is there. We will convert it to generalized coordinate. In general, by giving generalized coordinate, and we will simplify and we will keep in again. So that time we will get only independent coordinate. On according that process will be easy, and we will get the final answer. So we will do. Let me write. Our Alembert principle is like principle, and that is sigma number of particle is 1 to n applied force minus P is equal to 0. This is now how to solve. We will keep like separate I is equal to 1 to n, and it will come inside, so it will be dri minus P dot dri is equal to 0. Now we will take these terms to right side. This we will take in right side, so it will be equal to 1 to n, and the equation will be equal to P dot R dot. Now we will choose two parts, LHS and RHS. So first we will solve the LHS part, then we will solve right hand side part, and we will add both them. So let me take LHS part first. So left hand side part is will be del Ri is equal to sigma of I is equal to 1 to n particle. Here 1 to n is number of particles system in the system. So here it's equal to, will take. Then if I see this one, our main purpose is to change this del R2 into that independent coordinate or independent generalized coordinate. So how can we write? If any system is particle, we know the generalized coordinate Ri. Let me take Ri general, this one. Ri is a part for a particle or system, then there, which is a function of Q1, Q2, Q3, like Qn and T. So we can change it like this if I want to change. Del R if I want to change. So smaller displacement if I want, then I can convert it like this. This is the, if I take a partial derivative for this, then I can write Ri divided by Q1, and this part will be here D or Q1. Similarly, dri Q2, and this will be dQ2, and for nth particle it will be dn, and again it will be dqn plus del Ri equal to qn and dt. In this equation, many of the students, whether I used it before also, but many of you are getting doubt that how I am writing this equation. So for this is very simple. Actually, what I am doing, I am differentiating this equation in the form of a different function. Like if any equation, let me consider R is the equation which is containing x plus y plus z. Containing it's very simple equation, and m plus n plus t. These are the function of that. So R is containing here what I can write. R is having function x, y, z, m, n, and t. So while differentiating, how can I differentiate? If I do differentiation with respect to here, overall, how can I do? Means here, let me take it. If I am doing with respect to x, if I differentiate this equation with respect to x, then I will get dr by dx, and here I will get 1, which is direction is x-axis. Or let me take it x square plus y square. This is equation. So I will get 2x. Similarly, if I differentiate with respect to y, dr by dy, then I will get 2y, because this is the function of x. It will get 0. This will be 0. This will be 0. So only y term will come. If all are independent, be careful. If z is depending on y, then it won't come. Then I have to write dz by dy. The term will come. But this term I am considering for independent. So all these coordinates, the terms are parameters are independent coordinate. So for them, this will come. Similarly for z, I am, let me take for dr by dm, then term will come 1. If I add all these things, so no wait. If I want to write in this, then I can write it 2x dx. I can write. If I want to write it another way, this one, be careful. This one, if I want to write another way, I can write d by the partial derivative and dou by dou x of x square and dx. X square is what? This is the, and this one I want to say, so I can write what is the part of this. This is a function of r, and if I want to show that x function, I can. So rx divided by dx. Same thing. What did I do? Here also, I differentiated with qi multiplied with qi. Same dr with respect to dx. So either dou x dx, dou q1 dou qi, and q1 here also q1 will come. So if I am doing the second part, same thing. Similarly, if you want to see in this one, how can we write? We can write it like this. dr 2y, and this y I can take it this side, so it will be, and further if I want to move it, then I can write it like this. Dou by y square, and y square is there, I can write it r, function of r y, and this one divided by will come y dy. Similar. So this is the y coordinate, y parameter. This is x parameter, the m parameter, n parameter. All the parameters. If I add all the parameter, then what will I get? I will get r. So by adding, if I add this one, then m term will get, n term will I will get. So by adding, I will get this type of an equation. So what did I do? I am doing that same thing only. So now I think you got clear this idea that how I am doing, why I am doing these things. So these are the things. And now let me move it further. And so this is our equation. Then again I will create for partial derivative means that virtual displacement. It will be dou by dou ri q1, and here if you are saying for virtual displacement, you also can change there in that example also. So which one I solve now for means make you understand. So in here this one plus q2 del q2 plus like this plus q1, and this term will get 0 if I am taking for virtual displacement, because here dt will be 0, so this term will get vanished, so this term will not be there. Now if I want to make another change, then why I am solving again and again, because if we do practice again and again, you will get clear idea about this one, because all these things are new for you. So I take, then this is q1, q2, qn till and this is smaller. So if I take I, means I already am using here. So I will make this function of k is equal to 1 to, it is changing to n, k is equal to 1 to n, and this one for ith particle it will be qk. Now I will do, I will keep this value to equation number, where it this here. So if I want to change, you can write it, because take screenshot. So now let me